3.2 Measures of dispersion. So what is dispersion? In statistics, dispersion is simply how spread out the dataset is. Typically a higher value in all three of these methods or approaches to dispersion lead to a higher deviation or spread. So there's nothing you have to worry about in terms of like tricky numbers, like a smaller number. If a smaller number meant higher dispersion, then that would be kind of weird. But here they scale proportionately. Larger numbers means larger dispersion in all three methods that we'll get to today. Um, so a small standard deviation is typically when they're all concentrated in one area, like right here. And a large standard deviation is when they're over a large, or over this interval right here. So a range is the largest value minus smallest value, and it's horrible for measuring dispersion. It can measure dispersion if it's like a bell graph or if it's symmetrical, but when it has outliers, it's just horrible, and we'll get to that in a second. It's extremely susceptible, and because it only uses data points, so it doesn't represent, or two data points, so it doesn't represent overall spread well. Everything else uses actual measures of central tendency, but here we only use 2 points, which sucks. So take the dataset and let's ignore 0 and 100, only 45 to 50. The range is 5, but once we introduce these two outliers here, the range becomes to 100. The range got multiplied by 20, and this is not even 30% of the data points, yet it completely skewed the range. And the range is only attributable to the maximum and the minimum number, which is just unreliable. Never use this. I mean, you can use it, but it's not going to be very good. So now we go to standard deviation, and it measures how much data values deviate from the mean. Larger deviations are larger spread. So it's calculated by finding the mean first, subtracting the mean from each point of the dataset, squaring it, and adding those squared values. Then divide by the amount of datasets minus 1 if, not dataset, data points, minus 1 for correction in sample deviations. In population deviations, when you have all the data, you don't have to correct anything because you have all the data. Then you square root it. The squaring is because you have to get rid of any negatives, but I'm not exactly too sure how the exact formula was formulated. But you just square it to get rid of the negatives, you add them together, and we'll square root it. So these are the formulas here, and they look pretty complicated, right? We have the summation notation here. We have xi, and then we have another Greek letter right here, and we have we have a Greek letter right here, and it just looks super complicated. Well, firstly, it's important to note that summation notation is actually pretty simple. All it means is to use all the points in the data set and add them together. That's all summation notation means. I mean, it literally is in the name, sum. And n minus 1 is for the correction. So I'll give you an example here where we'll go to Sketchpad. And let's write a data point here. And we'll make this the number of points someone scores. Or yeah, we'll do points scored in a basketball game. So I guess we'll just label it as points. And then here we'll have frequency. So let's say a certain basketball team scores 15 points has scored 15 points 2 games in a row. They've scored 22 points 4 games, and they've scored 25 points 8 games. So first we have to calculate the mean, and everyone knows how to do that. You just calculate the worth. So 15 times 2 because there's 30 points, and then we do 22 times 4 because 4 games have had 22 points, and then 25 times 8, and then we just divide by the total frequency, which is just how many times the game has occurred, or how many games have occurred, and we'll get 14. And put this into your calculator, and you'll get 159 over 7. And we'll use this fraction for now to be as precise as possible. Then you take the points of the points. You subtract it by 159 over 7. And I'll show you how it is using the formulas here and what each represents. So here we have the data set or data point minus the mean squared. So then it's squared. And let me move this out the way. And you do this for all the data, all the different values. So 15, 22, and 25. I'll just delete this actually. And then you do 22 minus 59 over 7. 159 over 7 squared plus 25 over 159 over 7 squared. And here's where it gets a little bit different. So in samples, or in a sample set where you're trying to calculate the standard deviation, you have to subtract by 1. And you subtract the total, you subtract from the total frequency. So we have 14 here. It will be 14 minus 1. And then you square root it. That's the only difference. And if you want to get the regular standard deviation for a population, you just take that out. That's really simple. That's how you calculate standard deviation. I'm not going to put this in a calculator. But all the summation notation means is that you apply it to all the data points. So to summarize it again, find the mean using how much, or all the points scored here, divided by the total frequency, which gives you the points, average points per game. And then you calculate how much each data point right here deviates from the average points per game. And that's how you calculate deviation here. So the only difference between these two is that you subtract 1 from here. I'm not too sure why different lettering is used here. I'm pretty sure this should just be a regular n, but it is, so don't get confused on that. And variance is just the square of the standard deviation. Typically, standard deviation is better because you can apply calculus to it. But I'm not too sure how to do that at this point. I'm just measuring dispersion. And now we get to the empirical rule. And this just is basically like a test to see if it is actually a bell-shaped distribution. That just means 68% of data has to be within 1 standard deviation, 95 within 2, and 99.7 within 3. If the data doesn't match, it's not bell-shaped. So if the mean is 50 and the standard deviation is 5, within 1 standard deviation is 45 or 55. So if 68% of the data does not fall between these two, then that means it's not bell-shaped. At least 68% has to be between this. And Chebyshev's inequality, it looks rather complicated, but it's really simple. First, the formula is 1 minus 1 over k squared, as mentioned here. And basically, it calculates the minimum percentage of data that lies between how many standard deviations. So simply put, let's say we have 3 standard deviations. That would be 1 minus 1/9, which is 8/9. That means 8/9 of the data set falls between 3 standard deviations. Note that as k gets bigger, the percentage gets bigger. That's because as the range of Chebyshev's inequality formula, or as the standard deviation, and falling within standard deviation simply means that you're checking larger and larger. As the possible areas expand for your data points to be in, there's a higher chance for it to be there because you're checking more and more spaces. So that's Chebyshev's inequality. And these two are highly important. The empirical rule, you won't see that much, but it's just for bell-shaped distributions. This is for any shape. So